So the title of my talk today is Technology is the Answer, but What is the Question? And this is a quote from Cedric Price in his lecture in 1964 at the AA in London. And this is a quote from my colleague Hanif Kara, who is a great structural engineer. And he identifies that architects create great problems, and I would agree. And I think, to quote Bernard Schumi, architects or architecture should question rather than answer. And I think that's what I want to talk about today. And these are some of the questions that my work asks and that I like to think about. I'm not going to read them to you. I figure you're all literate and you can read them yourselves. But they're questions that drive the work as a broader scope, but then each project itself has its own internal questions. And some of the things I want to talk about are the evolution of technology from tool to technique to techne. And I think this is a really critical thing that I want to talk about, which is, I think oftentimes in practice we think of technology as tool, something that works for efficacy and helps us actually produce things more precisely, more accurately, more efficiently. And I teach at the USC School of Architecture and am heavily engaged in academia. I think academia oftentimes looks at technology as technique and really trying to find ways to produce novelty and explore to kind of drive different ways of applying tool to create specific ways of producing form or design. What I'm really interested in is what I would argue is the next step of this, which is technology as a form of techne. Techne being the Greek etymology for a way of thinking, right? And it's a way of thinking about making that is informed by tool, that is informed by technique. And so tool and technique become more, where if you look at Coltrane as the example, the saxophone is not a technique, it's not a tool, it's a way of thinking, and jazz is a reflection of that. We live in Southern California, or I live in Southern California. I don't know if any of you have traveled to be here, which I really think is defined by the case study movement and the rise of California modernism as a period of experimentation that really kind of challenged what the single-family home was inspired by technology and driven by responses to contemporary culture. What Los Angeles has become has been quite the opposite, right? And it's moved towards the model of kind of suburban sprawl and mass production and what I would call simply massive. Borrowing a little bit from what Dana was talking about, I think we can look a lot at what's happening with our colleagues in other industries and think about issues of mass customization and how technology can help us think about how we can produce things that are mass customizable rather than mass producible, as ways to also relate towards contemporary culture, and contemporary culture which now allows us to say, 50 years ago there was just blue jeans. Now there is literally hundreds of different styles of blue jeans. Farshid Musavi, in her book, The Function of Form, identifies that 50 years ago in America there was simply black coffee. And now if you go to Starbucks, there's officially 70 variations of coffee on the menu. Unofficially, I don't know how many variations of double pumps, triple pump, single filtered latte you can get, but there's a lot of variation which I think is coming into contemporary culture, and people want the bespoke. The other thing I want to talk about is the evolution of artifacts as prototypes for architecture. And there's a legacy of this in architecture in terms of thinking about material, technological, and formal experimentation at the level of the artifact, as shown here as a series of iconic chairs, that result towards the exploration of an architectural form that is sort of driven by the findings of the artifacts. The first topic I want to talk about is digital craft, and really thinking about how craft exists in a contemporary era, an era where we think of digital fabrication as a simple push of the button, and out pops this 3D printed artifact or laser cut artifact. But it's really, I would argue, a form of craft in itself. This is a chair that we designed for Stratasys. Stratasys is the world's largest 3D printing manufacturer, And we were asked to produce a chair for the Object 500, which is the world's first multi-material 3D printer. It's able to, normal 3D printers have one head, one nozzle, print at layers of 0.1 millimeter. This 3D printer has two heads. Each head has 96 nozzles and prints at layers of 16 micron. What this allows us to do is we had one head printing cyan, rigid, opaque material, another printing white, translucent, soft material. All I can call it is material because they won't tell us what's in it. It's just called it's their proprietary digital material. It is some form of resin-based material, but it does allow us to use those 96 nozzles, and produce material gradients through printing matrix, a printing matrix of those materials. And one of my very big pet peeves as a design instructor is that the 3D printer and its arrival has formulated a lot of people printing things that don't deserve to be printed. I had a student print the other day a flat sheet with 8 holes cut into it because he thought it was easier to print it than it was to cut it out. So what we want to do is say, how do you design a 3D print rather than 3D print a design? And a lot of the way we work tends to put the constraints of material and the constraints of fabrication first, and then part of that becomes the design constraint for the project. So this is a multi-position rocking chair, has an upright position, a lounge position, and we use this kind of gradient density of the material to support what's called asymptotic stability, which means that the rocker will always find its upright position. And because we can redistribute the mass of the chair through that density, we can place that center of gravity in a position where it will always find its upright position. We also use that multi-material property to kind of look at these ideas about gradients and thinking about the gradient condition, which is something which is not only visual, but also relates towards its structural performance and its ergonomic performance. And really thinking about this as related towards something which comes from nature, which is called durotaxis, which is the distribution of stiffness and rigidity within bones based off of the distribution of stresses. And so bones we think of as being kind of monolithic solid materials, but they're actually variable density materials. And so what we were doing was taking the 3D model of the chair, running structural analysis through Karamba, discovering the principal stress lines. These are the principal stress lines. Principal stress here is the composite, there is compression, there is tension, and you take the two and you map them out. And we use those as a way to drive this heat map, which then is using an algorithm called sphere packing, which we pack spheres into this and aggregate those spheres where the biggest spheres attract to different parts of density of the map, and we get this variable density mesh and produce this, which in the end killed our computers. The computation that was taking to do this, we could get to this point, but the point of actually producing something that was printable and completely connected was killing our computers, and this is where the craft comes in. The way we actually achieved this was, at this point, I had one of my interns spend 1 week solid of connecting and welding all of those vertices manually by hand, because we had the algorithm to do it, but it was too many vertices for the computer to weld. And then so it does, in the end, become a very manual process of craft, which gets subdivided into a series of parts. Those parts are, one, defined by the gradient. So you can see here, these are the steps of the gradient. But also what you see on the top is the parts in terms of how they fit inside the machine. And in the end, it's all 3D printed. As you can see here, it's essentially printed solid. So it's printed basically as a solid element with a support material to support all the unsupported cantilevers. Stuck inside an acid bath. That acid bath then removes the support material, so here it becomes porous, and then manually put back together by a series of technicians where the craft again comes back. So one of the biggest problems we saw with this project was that the cost of this chair, I won't tell you because I'm not allowed to, but let's just say it was more than my car. 75% of the material that we printed, which equates to 75% of the time, we had to remove. And we had to post-process, we had to get rid of, and then we had to basically throw away, which is much like the mold making process in composite materials or panel forming. So what we started doing was looking at how we could look at an ancient technique, the kind of idea of bricklaying, and the fact that 3D printing is essentially, in conceptual terms, akin to bricklaying. You're depositing material in horizontal layers incrementally. And that the idea of corbelling allows for unsupported cantilevers, where you can incrementally push over each layer based off of relationships between height to depth to width. And we started looking at how we could produce these series of tests, which are testing the limits of our 3D printing machine to produce unsupported cantilevers. And what we then did was produce this lamp, which was on display at the Design Matters gallery here in LA and is now at my house. But this lamp was a zero waste 3D printed object, driven by an algorithm which was constrained by the limits of the 3D printing mechanism to be able to support unsupported cantilevers. We turned off all the support functions, and now we have a zero waste 3D printed piece, which, as you can see, the spherical form is broken down into a series of parts. Those parts are actually an outer sphere and inner called isodecahedron, which I believe was 15 faces. What those 15 faces allow us to do is print each face from a flat bed, getting out to the spherical form on the outside. This is another project we did in London. It was a pavilion sponsored by Fiber C. Fiber C is a fiber reinforced concrete material, basically comes in 2.6 by 1.6 meter sheets, 13 millimeters thick. Basically, it's concrete plywood. It's reinforced by glass fiber and usually used for cladding and flooring and places where you want to have concrete finishes, but you can't have concrete. What we did was use it as a structural material and decide to use it as this kind of discontinuous concrete shell, all capitalizing on this material system and producing this kind of continuous form, which this pavilion was to celebrate the 10-year anniversary of the Design Research Laboratory, which at the AA, which is the program I am an alumni of. It was a design competition open to all the alumni of the program. We won the competition. This was the proposal at the time of the competition, a series of discontinuous concrete shells, or profiles all knitted together into a discontinuous shell. All at the time of the competition proposal, taking advantage of what we thought were the kind of flexible properties of this concrete material because they were fiberglass reinforced. And we spoke with the Fiber C technical team. They told us you could bend it, you could flex it, you could do all of this stuff. They said anything was possible, basically. So we proposed that it was going to be a friction joint driven by the bending to lock these pieces into place. All through a series of overlapping joints. Then we got our structural engineers, AKT, which is actually the firm I mentioned earlier, Adams Carrot Taylor, involved. We began running the structural analysis. Then they told us that Fiber C was full of shit and we could never do that. They would never sign off on doing a friction joint on this, and we were going to have to find another way. So we began working with AKT and developed this they developed this standalone C# plugin for Grasshopper, which allowed us to input our wire geometry, and it would reference the forces and the distribution of forces and size each profile accordingly at incremental points, so we got variable depths around our structure. And what we quickly found is that what we had sized at our initial kind of eyeball guess was wildly out of proportion to what was actually going to have to happen. And we fought long and hard through a series of iterations of warping, twisting, bending, trying to find different conditions that would reduce that thickness or that depth. and ultimately arrived at something which we found was workable, except for one problem, which was live loads. And so to avoid the live loads, basically we were able to get it to stand freely on its dead loads, but we could not accommodate, because of the increase of depth, the amount of wind load that was going to create racking. So we did have to have one dirty little secret, which is over here, which is the 3 continuous steel beams welded into place, which we painted gray and pretended were concrete and didn't tell anybody existed. All of this was produced through a set of an 80-page construction drawing set, which we were inspired by IKEA. We realized that traditional plans, sections, elevations were of no use. And the only way to put this thing together was to look at these kind of IKEA, sorry, it's not really reading real well, IKEA assembly instructions. And we basically put together this assembly package to put this entire pavilion together. Everything is CNC cut on a water jet cutter, which you see here, packed into here. We had a custom script written, which basically identified each profile in 3D space, identified the notches, sized the notches based off of the angle of inclination, so you could always pull them in and out, named each profile, named each notch, unrolled them into 2D space, nested them onto the sheets of material, and then reversed ordered the packaging of the profiles so that they would arrive onto site in construction sequence. What we forgot to do was get a parking permit for that truck. So when the truck arrived on the site, we didn't have a parking permit. They had to send the truck back. The truck came back the next day. What we then didn't do was lock up the forklift while the truck was away. The forklift had gotten stolen. We then had a 2-hour parking permit to get 850 unique concrete profiles off of this truck into this square. So our construction team of myself and my colleague Alan and the 10 students we were working with went into the AA and got about 300 students to come out and throw those 850 reverse order sequenced, perfectly ID'd profiles into 26 random piles and started construction. There were lots and lots of hiccups along the way. We were working with a team of students. Getting the site level was probably the hardest thing to do. We finally gave up on getting the site level and just started building. As we went up, you can see over the course of, I believe it was 4 weeks, the entire thing was constructed. Of course, with a little bit of help from our 1 to 10 scale model, which actually became far more useful than the drawings, where we were basically looking at the coding on the model as well as the coding through Post-it notes to the parts where we couldn't see. The entire thing was constructed, was supposed to be there for 3 months, was extended another 3 months, extended another 3 months, up to 1 year when the City of London would not allow us any more permit extensions. Became widely popular as a lunchtime destination and has won a number of awards. This photograph was taken from the night of the opening, or actually I would say the morning of the opening. It was about 2, 3 in the morning. You can still see the construction fence is up. What you don't see is there's 2 steel props inside here, which Hanif would not let us remove. He argued that this structure was not the structure that he had engineered because we weren't able to get a level site. There was a lot of movement in the joints, and some of the pieces we couldn't get into fix, couldn't fit perfectly, and so some of them had been kicked into place and things had broken, and we had a few errors. He argued it was not the structure that he had engineered, and he couldn't sign off on it and could not take those props out. What we agreed to do was take those 2 steel props out after the opening, leave the fence open for the opening. After the opening, close the fence, take the 2 steel props out. We did a 3D digital scan every day for 2 weeks, determined that the amount of allowable creep was within his tolerances. He agreed to sign off. We opened the pavilion and had to put up this stupid sign, which in London apparently is enough to alleviate all liability. That did not lead directly to this project, but in a sort of similar level, we were looking at how to create kind of complex form through complex three-dimensional form through two-dimensional profiles. This was a home office done for a private investment banker in London. This was post-2008, so he was still standing. But he was working from home and was an art collector and wanted a piece that was somewhat a piece of art in itself, but also disguised all of the kind of requirements he needed to function in his home office, from his storage, his filing, his printer, his paper shredder. The paper shredder actually feeds through one of these slots over here, and you can see the cabinet for it down here, and it feeds through one of the slots on the top. And so this project really was a chance for us to kind of take some of those ideas from the previous project and explore them in a more tactile sense of something that somebody would touch and feel, and thinking about issues of trying to capture the light of this really tiny room. We have all the storage elements there where his filing and storage sits inside. There's a lot of issues about trying to prefabricate all of this. Everything was prefabricated off-site, CNC milled, nested onto sheets of laminated birch plywood, trying to capitalize on the natural day lighting. But everything is also prefabricated into these modules and delivered onto site, where the entire process of fabrication took us about a month and a half. Installation took us a little bit over 4 hours. So basically, everything is dry hung. We have a series of Z-clips which anchor into the wall behind, and then these very big, heavy plywood modules or plywood things are brought in, prefabricated, and assembled into modular components, and just dry hung onto those Z-clips. And then what you see there on the outside is a graphic pattern of the world map. And that graphic pattern of the world map, because everything we have to achieve the effect and to achieve some kind of reduction of cost, we alternated the spacing of the panels to open it up a bit and use less material. But which led to these open ends, since everything's only fixed at the back. So that graphic pattern of the world map is actually our structural bracing, and it keeps us from having any kind of lateral movement. But it also allows him, who's an avid world traveler, to have a world map on his wall, just like he wants his filing and his storage there, but he doesn't want to see it. He has a world map there, which he only sees when he chooses to see it. And so here you have the project and some of the drawings which we produced for it. This is the process we're doing to nest all of the profiles to try to get maximum material efficiency. So when you see it, it actually looks like it's hugely wasteful of material. We were trying to maximize as much material as we could, and so you can see for the amount of material we used, it's actually highly efficient. Another issue which we're exploring in the office is what I call performative patterning, and it's very much inspired by the painting in the background you see here is from Bridget Riley, the great British op artist, and really thinking about patterns as something that I think are essential to architecture. There really is no such thing as monolithic anything. Everything's made out, everything we construct has to have joints, have to have seams, and I would like to take advantage of those joints and those seams to think of patterns as something that don't have to be endlessly repetitive, but can actually be visually engaging and not responsive in the sense of moving, but responsive in the sense of appearing to move to our movement. And that would be about, I'm really interested in moire patterns. So this is a project we did in Lampong, Thailand. Joey, who's out here in the audience somewhere, he did quite a lot of the modeling on this project. And this is a facade. I'm not taking any credit for the architecture, like we just did the skin right here, or definitely not the landscaping. But the project is a facade that sits on the side of a freeway for this shopping center, and what we really wanted to do was say that people are moving at mostly 80 miles an hour past this, and trying to get some sort of visual engagement where they didn't read it as an object, but they read it as a field that would draw them in and get this kind of changing, pulsing condition as they moved across it. So here's the site as it sits on the freeway. We have this kind of idea of this grid moving from being completely fixed to a free-form grid to a rationalized grid. And that rationalized grid moves from the diagrid to this kind of evolving variation, which in the end produces this kind of gradient effect between a white field and a red field. All of this is done through a series of parametric models, which we're able to manipulate real time and kind of find these relationships. It's all driven by geometric relationships. And it's basically by changing those relationships and, say, changing the radius of the circles that drive the position of that diamond changes the scale of that diamond, and everything is connected, producing this kind of knock-on effect of the field. In the end, all of that is processed through a process of rationalization in producing exactly 5 different panels, which, because we can flip, mirror, and rotate, we're able to get more variation. We produce this kind of color map, which helps the contractor lay out exactly how to place those pieces. And in the end, we have this effect where, as you can see, when you look head-on, you only see the shadow. As you move across, the colors start to appear. And then you get this kind of pulsing effect as you move across the field. All of this is then backlit with a series of phase-changing LEDs, which basically also help amplify that pulsing effect by changing colors throughout the night. This is a project which we just recently completed. It's for IBM Watson, and it's looking at the pattern as an opportunity to, one, produce the sort of dynamic moire spatial effects which we're interested in, but 2, as an opportunity to think about data as a narrative. And Watson, if you're not familiar, is the cognitive computing machine learning division of IBM. And what Watson is able to do is deep dive very, 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 very large data sets and return that information to help people make decisions. So this is the showroom for the San Francisco Watson Experience Center, which is dealing with e-commerce. So when we made the pitch, we appropriately put, the people from Silicon Valley into our renderings. That went really well with them. But what you see here is that we've basically used Watson, and we asked the Watson analytics team to help us and made it a collaborative process where they gave us this deep dive analysis of 3 years of e-commerce and its relationship to mobile phone sales. And we were able to convert that into a series of heat maps. Those heat maps then drive a topography. The topography then we analyze that topography for mean curvature, Gaussian curvature, identify topographic contours, identify flow analyses, and we're processing this heat map into a series of geometric issues. And those geometric issues we then map and produce 2 different patterns. They're actually mapping the exact same set of data. One is the kind of Delaunay version, the other is the Voronoi version, and when we overlay those 2, we get this effect, which is the same pattern, and you can see the intensities. This right here is the weekend. We had to shift the map because if you put the weekend at the bottom, it was not so interesting. So we shifted it, so I think it starts at like Tuesday and then ends down here. So this is Friday, Saturday, Sunday, and so you see that internet sales increase during the week, and as you move across, there'll be moments where you'll catch glimpses of big intensities, and that'll be like Black Friday or the day after Christmas where you have these big sales. Here you can see how the 2 layers overlap, and because of the 2 layers overlapping but being slightly off, you get this kind of kinetic moire effect as you move around the wall. And this idea of geometric logic really drives all the work that we do, and thinking about geometry that's defined by relationships rather than geometry that's defined by dimensions. And this is something that really has driven pretty much everything that we do. This project, in large part, because of the fact that we're working with a local architect in Thailand where we hand over after DD and then they take over. And as all of you know, there's a huge amount of coordination to be done after DD. A huge amount of revisions to be made, and a lot of moving parts. And so one of the things that we wanted to be sure was that they understood our drawings not as a set of fixed dimensions, but as a series of driven relationships. And identifying the difference between a driven relationship and a driving relationship was really important for us, so that they're able to identify, I can move this, which is going to move that. And if I move this, it's going to move that. And I need to maintain tangency, I need to maintain equal distance, I need to maintain all of these things to maintain the design integrity. And so part of it for us was literally, rather than dimensioning numbers, dimensioning relationships. So this project sits on Planchet Road, which is the major retail artery of Bangkok. It's hugely intense. This is our client's tower, that's his mall, that's his hotel. This is his city. It's 6 million square feet of retail, office, hotel, conference center. There's probably other things that I don't know about going on inside there. We did this, so it's 12,000 square meters against that 600,000 square meters. So I like to call it the punctuation on the paragraph. And when we started the project, the local architect gave us these two sketches to say that we want to maintain those three connections from those buildings and have two sort of atrium-like conditions here in the middle. So what we did was work with that, and can you click on this so that okay, well, if it were playing, you would see these boxes shifting and moving and trying to find different configurations and arriving at this one. And what we were able to do was sit there and drive the relationships between those masses, have that connected to an Excel chart, and real-time sit down with the client and discuss the knock-on effects of their lettable square footage when we made design decisions to shift that volume or shift that volume. So in the end, we arrived here. We look at trying to capture those intensities from the retail promenade and that activity, have that carved through the building, and then reveal a sort of warm interior inner flesh, which was the timber cladding. These are some drawings of that intensity and the kind of facade design. And here we have the completed project. It's won a number of awards, most recently, I think, the best retail project in Asia by a magazine. And here you see some of the interior shots. So this is the one actual interior side, and then this is the protected outdoor courtyard. So what you see here is actually a series of retractable fabric canopies which open up, and some of the detailing on the facade and the perforated aluminum composite panels and the way it meets the timber trim. This project is one which was a competition which we did not win. If you guys are on Instagram, we have a hashtag of ours, which is another failed competition. If you check that, you'll see lots of our work. But this is a competition which we didn't win. It's a library in Daegu, South Korea, and really thinking of the library as an extension of the landscape of the park that it sits within. And thinking very much about being inspired by Claude Parent and Paul Virilio's treatise, Architecture of the Oblique, and the idea that an oblique architecture, an architecture of only horizontals and obliques, would allow every surface to be usable. You can lean on things, you can walk up things, you can sit on things, but also allows the way that a person navigates architecture to be like water, right? You navigate by gravity, either against gravity or with gravity. And we started this project by looking at how to take this diagonal path connecting the residential area. I can't read, actually. So one of those is residential, one of them is the park. Okay, now I can read park, residential. This diagonal path through here, we pull up these two cores and start knitting these surfaces together and go through this process of relaxing these surfaces, which is called dynamic mesh relaxation, into this continuous form and continuous section, which means it's a library that has no rooms, just continuous spaces, but a series of soft divisions between those spaces, and a library which basically moves up from this landscape. You enter underneath the library, enter up, wrap around, and arrive at the roof terrace on the top. And then an interior which has these sort of capitalizes on that sectional change, to embed a series of what we call ergonomic landscape furnishings. And those ergonomic landscape furnishings are driven by the section, and as the section slope changes, sometimes they're ramps, sometimes they're stairs, sometimes they're shelving with seating, other times they're desks, and they aggregate to create these different conditions and create these different landscapes. And part of the proposal was saying this is a library of the 22nd century, not the 21st. Books are becoming obsolete because we have a wealth of information at our hands, but books are special and they're different. So instead of having a library that is a collection or archive of every book, it's a curated selection of special books that are there for you to discover. Needless to say, we didn't win, but we learned a lot. And that process of exploring mesh relaxation really informed us to think about this topic, which is informed form, and thinking about extending the sort of modernist ethos of form follows function to think about, can function be more than utility? And in this case, can function also be performance? And can performance be one, structural performance, environmental performance, and also my favorite, visual performance? So we're really inspired by Frei Otto and his experiments with soap film, and how he was looking at how to form find these minimal surface structures through looking at the relationship between soap film and a perimeter frame, the perimeter structure. And we began experimenting in Kangaroo, a plugin for Grasshopper, which is a plugin for Rhino. There's a whole zoo out there of animals that plug into one another. It's a little bit incestuous, but it produces really interesting results. And what we're able to do in this software is simulate physical forces onto geometry. So clearest example is up here. Like, you can simulate that this thing is actually dropping and producing a catenary curve. And in the end, we were able to test these sort of ideas about the minimal surfaces that Frei Otto was testing manually. We were able to do so in a digital format. And that led us to this. And this was a competition which we won. It was a pavilion for Volvo. Volvo was promoting this, which is the Volvo V60 plug-in electric hybrid diesel car. They started this open international competition, attracted over 250 entries from around the world. The only requirements were that the pavilion needed to, one, represent the three modes of the car: power, electric, and diesel. Oh, sorry, power, hybrid, and electric power, hybrid, and diesel. And be demountable within 1 day and assemblable within 1 day, and be able to put inside a shipping container to be taken to different trade shows around the world. So here you can see some of the results of the other shortlisted winners. Basically, everybody looking at it as a prefabricated garage. What we were looking at was, how could it be more of an accessory rather than a destination? The garage being a destination, the backpack being an accessory. And if it's an electric car, can it be an accessory that not only travels with the car, but also charges the car? So our goal was to have it, one, fit inside the trunk of the car, and two, charge the car. And the result was this, which is the pavilion.
In spring of 2013, Volvo Italia and the Plan magazine launched the Switch to Pure Volvo Open Architecture Contest to showcase the new Volvo V60 plug-in diesel hybrid at undercover trade shows and open-air venues in Italy's public squares. Attracting over 150 entries from around the world, the winning entry was the Pure Tension Pavilion by Synthesis Design and Architecture. The entire pavilion assembles and demounts in less than 1 hour and fits in the trunk of the car.
The Switch to Pure Volvo competition, organized by the Plan on behalf of Volvo, was interesting to us in terms of the kind of questions and challenges that it raised.
They required that the structure is something that was easily assemblable, easily dismountable, and could travel with the car, and was an iconic structure that could really showcase the car. We saw this as the perfect opportunity to apply some of the research we've been doing into dynamic mesh relaxation and thinking about how we can look at fabric structure in terms of thinking of something that's lightweight, portable, and easily collapsible. So the original idea of this was that
the structure would wrap up and bundle into like a little package, like a laundry hamper, and just kind of pop open, which would have put us well out of budget. So we ended up moving towards a CNC bent aluminum frame. So it is slightly outside of the final shape it's going to take, but it gets tensioned into position by the skin.
On my spare time, I like to go backpacking and camping. So a lot of the stretch fabric aspects of it was something that actually was very attractive to me because it's something I was so familiar with, that lightness and efficiency. And also the elegance that the combination of the simplicity and sophistication conveys.
We took that a step further and began thinking about it as a charging station for the car.
We wanted it to actually be integrated into the whole structure, that it's not just a plug-in interface with the power, but it actually produces its own power.
So when we saw this design, obviously, there were a lot of things that we saw that fit together.
After the winning of the competition, we went through a process of rationalizing the geometry to make it more buildable. Worked very closely with our structural engineers, Bureau Happold, which are based here in Los Angeles and Culver City. And then we started working with Fabric Images, who are based in Chicago.
The design idea behind it is this idea of pure tension. We weren't sure how we were going to do it, but we'd started. And we started figuring out what worked and what didn't.
Where we're at right now with the frame is that we have through bolt connections. The next step is to drill out and countersink all the connections for sex bolts, so it'd be flush connection, so there'd be nothing protruding.
And eventually, between the seamstresses, between our CAD guys, between myself, we figured out how to do it.
Ascent Solar provides us with these, which are flexible photovoltaic panels. So unlike normal photovoltaic panels, which are extremely rigid and extremely heavy, these are extremely light and flexible.
Because of that constraint, we had to choose a lightweight, 70% open mesh. And what's interesting about mesh relaxation techniques is they use the natural qualities of the material to create a shape. What's interesting about this structure is it takes the natural qualities of the Volvo and lets that inform the formal qualities of the structure itself.
The entire pavilion, in terms of the skin, fits into a small box, whereas the perimeter frame, because it is a kind of slip-fit tube, like a tent, demounts and will fit into the trunk of the Volvo.
There is a positive side in that it will provide solar energy, but there's a negative side in that it heats the car. And just cooling the car to a comfortable temperature requires a lot of energy. So anything that could reduce the solar heating of the car while also providing the electricity that the car wants is a win-win situation. And also to do it in such an efficient way and in such a beautiful way. That was something that our innovation team always looks for, and it was great that even though we had not found it ourselves, that we could support the innovation process that could enhance our products and hopefully enhance the world at large.
The interrelationship of our structure and the car is something that kind of drew attention to the car and also allowed you to experience the car in a new way. I think what's really surprised me in this journey of producing this pavilion and winning this competition has been just how forward-thinking Volvo has been in terms of engaging us as designers and giving us the freedom to do what we're interested in and really pushing the limits of what our fabricators are able to do. And they've been very supportive of that and engaged with us in the entire design process in terms of producing something that we think is really an amazing concept that we hope can be applied towards future products and future opportunities.
So the project was developed, as you saw, originally as a kind of free-form geometry that responded to the three modes of the car, three points up, 3 points down, creating this kind of complete structure. At the time of the competition proposal, we had proposed that it would be a continuous composite carbon fiber pipes, which could bend into place and allow us this kind of bending moment of it all springing open. We went through this process of form finding and testing both in digital as well as physical processes, and working with our structural engineers, Bureau Happold, to do the actual engineering and precision form finding. One interesting note here is that Bureau Happold kept telling us how our form finding process, which is done through Rhino, which is a relatively inexpensive program, and Grasshopper, which is a free plugin, and Kangaroo, which is another free plugin, was amateur and not at all going to be accurate to the form finding results. While they're using NDN membrane, which I'm sure there's some engineers out here. I don't know the exact cost of the software, but I think it was something like $30,000 a seat. But we were able to get within 2% to their actual form finding results, which I was quite pleased about. I will say I needed that 2% because I'm not going to take the liability, but I was very happy how close we were able to get. What started off as free-form structure, we rationalized into exactly 5 arcs. If any of you have done CNC pipe bending before, I had never done it before. Our first quote was astronomical, like way out of our budget. So I sat down with our fabricator and I said, okay, explain to me the process of how you are billing for this pipe bending. And he's like, so we take your free-form geometry, we convert it into arcs, then we take each arc and we program each arc into the machine individually. And I said, okay, how many arcs are we at right now? And he said about 1,500. I said, okay, give me a few minutes, give me a night, we'll come back to you. And we were able to turn it into 5 arcs and saved quite a bit of money. We then took the skin, and we knew that it was going to be driven by the sun. We did not know what orientation it was going to sit in or where it was going to sit. And so what we did is, because this competition was for Volvo Italy, we chose Rome as the center of Italy, put the pavilion in the center of Italy, and did solar incidence analysis for 365 days of the year, for 360 degrees of rotation, for 8 hours of the day, and averaged that into this heat map, which gave us the kind of points of greatest solar incidence, which we then converted into this kind of gradient graphic map, which basically maps out the positions of all of the solar panels. All of this is then unrolled into 2-dimensional strips and tailored very much the way you would tailor a suit, right? And given to a series of pattern makers. Here's the CNC pipe bending. Here's the assembly of the pipes, putting it all together. This is the first fitting of the project, and here we have, this is the part we did not manage to finish on time. We finished it in terms of it working, but the original idea was that all of the wiring was going to run through the seams like conduit. But we didn't have enough time to figure that out and ended up having these really unsightly wires running everywhere. And here we have the final pavilion. So I'm going to end with this slide, or almost end with this slide. I have one more after this. I've ended every talk I've ever given with this slide since 2008 when I first started giving lectures. At that time, I was on a panel for a conference called Digital Architecture. And so I thought it would be quite provocative to end a conference titled Digital Architecture with a slide that crossed out the digital. This photo here is of the very first car, which at that time was called a horseless carriage. We talk now today about digital architecture, but it's really not digital architecture, it's just architecture. Just like this is not a horseless carriage, it's a car. And I think that's a lot of the things that we have to be doing as architects in terms of thinking about the tools and the techniques that we're using, is seeing them as tools and techniques for architecture, not a different type of architecture, for architecture. But also that they are producing something and working in a paradigm that is slightly different to a pre-horse era. So one of the things I'm really fascinated is sort of childhood development. I have 2 small children. And the fact that if you give a child today, I haven't actually run this test, I read this, that if you give a child today take them to a rotary phone, they not only don't know to turn the numbers, they push the numbers as you would expect it. But what I found really interesting is they push it with their thumb, right? Which is, now people know buttons like this, right? And so the first reflex for a child to push a button now is like this. And so there's a changing paradigm that's happening in terms of the way that people perceive one, design technology or the ability to design. The other is how we occupy space and how that changes us as people. And so I think that's something for us to be very conscious of. I'm going to end with this, which is a quote from Neil Denari. I wrote this down. He was giving a lecture for my students at USC, and I was just so struck by what he said. And I would say that in the end, this is really what my work is about. It's not about the technology. It is what I think all architecture is about. Thank you. Thank you.
So, I think we don't have much time for questions, but if anyone has a burning question they would like to ask, please raise your hand, and we will take the time.
Yeah, I think I ran over my slide.
No, that was wonderfully inspiring and very informative. Yes, Wyatt has a question.
Thanks, Alvin. That was fantastic. Really inspiring stuff. When I look at your work, I'm constantly amazed by the seeming complexity that goes into it, the thought, obviously, and this kind of interplay between design, craft, and fabrication. For those of us, I think many of us in this room that function more in the traditional mode of architecture, I'll say, and the delivery process, what kind of advice might you have, because you bridge academia and practice, for the way that you work in your office?
I mean, the way that I work is probably not altogether too different from the way that most people work. I mean, design is design. But I would say that we are very much trying to identify the fabrication and the materiality as part of the constraints for the design from the beginning, rather than, and particularly with the type of work we do, I think there is a tendency for a lot of the more formal work that exists out there to go through a process of design and then into a process of, okay, this is how much it costs to do it with this material, this is how much it costs to do it with that material, this is how much it costs to do it with that material. And then it becomes a kind of materialization by Darwinism. We tried to breed it from the beginning rather than at the end. And I think that's something that for us is really about trying to, whether it's about the material or the geometry, the fabrication, or the problem itself, really identify the constraints of the project and turn it on its head, which is what I guess we're trying to do. I don't know how successful we are in all of those things. But I think the major thing would be about being literate about the technology as a form of design, conception, rather than just as a design representation or realization, or like the people. I grew up in an era. I graduated from USC in 1998 from my undergraduate, and so I was at the beginning of the CAD era, and my training was with the hand and the pen and the pencil, and you were always taught to think through the hand and think through the drawing. And I've been fortunate enough to go back to graduate school in an era where I was able to learn how to think through the computer as well. And both are thinking processes. I think anytime you make it an automation process, then it's a problem. And I think that's what I would really push. Yeah. All right, thank you.
Wonderful. Thank you.